Welcome to the insertion sort video, everyone. Okay, so what is insertion sort? Insertion sort is a sorting algorithm where elements that are greater than the original element get pushed up and the element gets added in the blank spot that is made. So let's just view this with an example. Let's say we have a list or an array containing these elements. I know this. Okay, so this is our initial list. Now with the insertion sort, we start here. We start looking at the first element. So our I would be 1. Let's check if you don't know what I is right now. Let's just use an arbitrary thing right now. But basically, we start here, and then we compare it to j value, which we can also just set to I minus 1. Because I was going to be the element right before your I. If this value is greater than this value, so if 4 is bigger than 8, then we'll push 4 here and we'll write 8 here in the blank spot that gets made. And we're not going to do it 4 because 4 is not bigger than 8, but you'll see that. What I mean by that is 7. Right? So this will evaluate, nothing will happen. So then I'll keep this. We take this and then j pointer will point to 8 now, and I pointer will point to 7. And then when we're here, well, now in this case, is 8 bigger than 7? Yes. So we actually do have to do I wouldn't say swap, an insertion. So we're going to store 7 in some temp variable, because basically what we do is we take, how this sort works, it's just a thing looks like this, right? In the code, what actually happens is the 8 value here, because we need the 8 value to be here, right? We need all values bigger than 7 to go up a space. So if 8 is going to go up a space, then look, it's going to actually cover 7. But that's expected. That's why we make a temp variable to store 7. So pretty much you'll have that 8, and then in the blank spot are the original 8 is where the 7 will be. You can look at it as where the J is. Well, I said it. No, you can't. No, you can't look at it where the J is. That's wrong. Listen. Okay, but let's keep going. So I'll take this list of numbers. Let's copy and paste it for the next iteration. J moves up 1. I moves up 1. So now we're doing the same thing. Well, how many numbers is we need to push tree back, right? And all of these values are greater than tree, so all these values are gonna move up 1. And we're gonna fill tree in the blank spot. So what would that look like? We'll store a tree in a temp variable so we have access to it later. Because the way we typically do this, the way we move things up, right, is we just copy over the old elements index to the index plus 1. So that's gonna be like that. This is gonna be like this. And this is gonna be like this. And so what we do now is we take J and move it back here. And you'll see, yeah, you'll see later on how this actually works. How we J back here. Hopefully you're understanding everything so far. So let's keep going. If you're confused on how we get the tree back in place, Don't worry, I'll explain it soon. Let's copy and paste that. Let's take our values. Let's move them over one. And then let's see, say bigger than 2, yeah. All these elements are bigger than 2, so we're going to do our process again. Just take these elements. Well, first, we're going to store 2 in a temporary variable so we don't lose it. Then we'll just take these elements and paste them over. I'll actually show it. Right, so 8 like this, 7 is going to go like this, 4 like such, and then lastly 3 like such. I don't want you to think it's all the new element always goes, or the element that's inserted always goes to the beginning. That's just the pattern right now because our elements are so low. Let's keep searching. So in our next iteration, j is pointing at 8, I is pointing at 1. Well, I is bigger than 8 and pretty much all the elements that come before it, so we're just going to copy everything over again. I'm just going to do like this time. And you have one here. I didn't store in a temp variable, like I said, but you do. Like before you insert it, before you do the swapping, you store you store the variable you're swapping, or pushing back, inserting, etc. in a temp variable. Because look, if we didn't have the temp variable, there's no copy of 1 anymore, right? Because 8 consumes that. So just make this 1. Okay, let's keep going now. So I'll take all of this, copy and paste it here. Take our I and J counties, I'm going to move them over 1. Right? Okay, yeah, so the next step that we said we're going to do is take all elements that are greater than I, in this case 7, 8, and we end up push them up 1. And before we do that, we're going to store 5 in a temp variable. And it's variables, we're going to push them up by 1. And then, right here is where we'll store 5. Again, if you're confused on how this temp swapping actually, or how we get the 5 back in the correct position, I think understanding that the elements are copying over makes sense. Understanding how 5 happens, because here it doesn't really click right now. It will once we talked about this more of the code. Okay, so now looking at 8 and 9, well, 9 is not bigger than 8. And I mean, honestly, you won't have a situation, if you put merge sort correctly, or sorry, insertion sort, you'll never have a situation where this is smaller but then this is bigger. Because that defeats the whole idea of insertion sort. Insertion sort, like sorting the elements as you go, you know what I mean? So here's our next set of numbers. Let me delete all of this. That's too much. Access. Right, we're gonna push our 8. We're gonna push our J. We're gonna push our I again over here. And now 6 is smaller than a bunch of these values, so we're gonna store 6 in some temp variable. Take all the values that are bigger than 6 and push them over 1. And then here we're gonna store 6. And then, well, I is at the end. There's no more room for I to move in the array. So we have successfully sorted this. Okay. So if we think about it in a code view, well, when we can view all of these ij movements, all of these is really occurring in some sort of loop, right? We could just have one loop that iterates and changes for I each time, right? Because j is related to I, so if I changes j, I'll move with it. So you can have one loop that does that, like a bit, outer loop, we'll say, because it'll be responsible for I/J handling. But do we need another loop in this code? The answer is yes. We need a code to handle the swapping, right? Right here. To swap 8 and 7, we actually need a code for that. Let's think about what actually happens there. Let's look at a bigger one. Like, let's look at this 6, 7, 6. Oh, oops. And let's look at this 7, 8, 9, 6 one. So what really happens here? Well, first of all, we're going to use a while loop for this. Loop for the swapping, because if you use a while loop, we don't know how many iterations you need to go through. And we can't really know how many variables we have to push up, right? We can't really understand easily like how many numbers are bigger than this number. So you can see it numerically, but on a code, could you write an algorithm for that with just a for loop? Probably not. So we just use a while loop. But what should our conditions be, right? We can't go to forever. Well, it makes sense that one of our conditions should ensure that the array element at j is greater than the array element at, I guess you could say our temp index. We store the reference to that temp value, right? Because if this condition is false, then if j is not greater than I, or greater than temp, then that means we shouldn't swap anything at all, right? That means the element before, or like this, right? The element before I is good. Of course, we need another condition, which would be, and this one relates to the whole idea of getting an element back in its right place, and then be like, and j is greater than or equal to 0. So what does this actually do? Well, here. So this is the program, right? So something else must happen here, right? Let's break down 896. So take these elements. So let me show you how this swap actually occurs. So this condition is met because currently our variable, I just shouldn't really need to be j. It could also just be like, oh, I forgot to swap. I'm talking about this iteration. Right. Sorry, when j was here and I is here, we're looking at 8 compared to 9. When j is here and I is here, we're looking at 9 compared to 6. Right? Well, 9 is definitely bigger than 6, so and j is not equal to 0. Our counter, not the value, j is a pointer referencing 9. So what we can do is we can swap it. So, and remember what I said for swap, it's basically just taking this value and pushing it over to the next one, right? So that might look something like r j plus is, if you want to do j plus j plus 1 is equal to r of j. Right, because what actually happens in this line, if you think about it logically, in this line, we go pi and line. That's what this code does. It kind of copies this over, so the pi number saying it's actually happening, right? Well, then our temp variable, right? Oh shoot, we need one. Well, then it kind of makes sense to define a temp variable. It should probably be defined in the outer loop, right? Because our inner loop is constantly changing, right? If we put it in here, it would probably and it could actually end up dereferencing the correct temp value. We want this temp to always point to 6. I want to always point to 6, because I'm setting it to 9. We're setting it to I. Putting it I because I was 6, right? Well, now it's not, but it was 6. And we're keeping it outside the loop because we want it to be 6 while this loop is happening, until this loop is done, so we can plug it back in, right? And then what happens? Well, we actually shift I minus 1, and then we compare again. So if we write j minus, and then we'll do this swap. We're not, is 8 bigger than 6? Yes, it is. So we'll swap it, push it over. And then I think we had 7. Yeah. 7 here, and then I think it was 5. Let me double check for us. Yep. Okay. So we're gonna push j back again. Check out the conditions. Well, 7 is bigger than 6, and j is still bigger than or equal to 0. So we're allowed to swap again. I'll copy this, I'll paste this here. I'll move back 1. Okay, so j is here now. Is 5 bigger than 6? No, it's not. We're saying so we'll only ever hit this case. So we actually would run it in the beginning. Here in the beginning, like over here, right? Well, not in this example per se, because 4 is less than 8. But if the original element was bigger than the second element, then this condition would be met. J will be equal to 0. Anyways, so now we're here. We've got here, right? Well, we can actually just assign the value of j plus 1 to our temp. Because look, that's that empty spot I was telling you about, right there. So if we just assign the value j plus 1 to that 6 that we stored, it'll be perfectly coded. Okay, so now we have the basic idea of how we're going to code this. Let's actually code it. Get rid of this. So we're going to say 4 and I, and we're going to start I at 1 because I is, no, that's when our point is. I should start at point at 0. Remember, we started I at 1. So we can say int temps URI, right? And then we also need to find j. I'll define it above, so int j is equal to minus 1. Right? And we can say while j is greater than equal to 0 and our j is greater than d10. Right here, I said temp will point to a reference, right? So let's make it I. So we'll say R of temp. Well, then what we can actually just do here is just, if this is true, we're going to do that copy line to R j plus 1 j. And here we're going to say R j plus 1 equal to R of temp. And then lastly, we need that j minus clause. And then, so if we go up here and we go to insertion sort, and here, we get the set elements that we used. So we used 487 321 596. So 487 321 596. So when I run this, you'll see our algorithm here. Okay. Let's see where we might have gone wrong in the code. This probably have to refer to I itself in its entirety. Because actually, that's probably, yeah, that's definitely it. Sorry. Okay, run it now. Yeah. So the reason why I can't make this an index is because we talked about it, right? When you're doing your swapping, like when we did that 8 to 8 or 9 to 9, whatever, right? We only had 6 here originally, something like this. Say, we took that 8 and we took that 9 and we put out that 6's value. So if we were then to still use that reference of I, which would be pointing to this still, we would get cooked, which is why we need that temp variable, because the references to or what I and J store change over time. So we can't trust them to keep our six safe. Okay, that's insertion store. The last thing we need to do, of course, is talk about the time. Over here. I'm going to talk about the time slash space complexity. Okay, so what does that mean? Well, what would it even be for this algorithm? Well, just like the other one, it's going to be average time. It's going to be O of n squared because it is still a nested for loop. Your worst time is O of n squared. But then your best time is O of n. And if you think about it, the best time O of n actually makes sense because if your array is already sorted, in an insertion sort, this inner loop will never get called, right? Because it relies on the fact that your element before your I is greater, right? So if your elements are already sorted, that won't occur, right? So it makes sense why the inner loop never occurs. We're just running one for loop, and just running one for loop at a time complexity of O(n). Okay, the space complexity, your best is going to be O of 1. Your average is going to be O of 1. And then your worst is also going to be O of 1 because, again, no stack traces, no more calls made from it to the stack trace, nothing's recursive. We're just working with one array. Okay, and this was Insertion Store. Thank you for watching.